Sounds good.
All right, welcome. If you're just logging in, we'll get started in 2 minutes. Welcome. If you're just joining us, we will get started in 1 minute. Good morning, good evening, good afternoon, whatever time zone you may be at, welcome. Welcome to today's educational program, Why Open Source Works for Industrial IoT, brought to you by IIoT World and sponsored by Influx Data. I'm Lucian Fogoros, and I'm the co-founder of IIoT World. On behalf of my team, thank you for joining. Our co-founder, Karolina Rudinsky, will monitor the online channel, so feel free to send your questions in the Q&A section or via the social channels such as Twitter or LinkedIn, leveraging the hashtag IIoTAI. I'd like to introduce our moderator, Greg Orloff, our senior analyst and CIO, your host for today's virtual conference. So Greg, welcome.
Thank you, Lucian, and hello, everyone. Before we get into today's session, please allow me to give you, and those that are joining us for the first time, a little background. IIoT World is a digital media publication that covers the economic and technological implications of the transformation taking place as industrial IoT proliferates throughout the enterprise. IIoT World combines journalistic coverage with data analysis to expose the stories, players, trends, and innovations that shape the IIoT. IIoT World was recently ranked by K-Core Analytics as the #1 global influencer on several topics that include industrial IoT, smart manufacturing, ICS security, SCADA, predictive analytics, and predictive maintenance. Our mission is to help companies create a culture of innovation and connect the smarts, industrial technology, manufacturing, sensors, and the CXO decision makers who seek these solutions. Now today we have an exciting panel that personally I've been looking forward to with representatives from Intel and Influx Data. Our agenda today, basically the industrial world has a long history of modernizing their process controls in order to keep production running efficiently and safely while minimizing downtime. Yet many are locked into established data historian solutions that are costly and lack the methods needed to provide innovative and interoperability and innovation. In contrast, open source software, which is built on the foundation of community, inherently provides diverse design perspectives not available from a single software vendor. In this 60-minute webcast, our speakers will examine what the existing solutions lack and review a few open source projects that should be considered for future success by operators. Key topics we will cover today are how IIoT is innovating by using open source tools, how to get real-time visibility into stacks, sensors, and systems using open source tools, methods to seize new opportunities by capturing and analyzing untapped data from virtual and physical assets, the business value of IoT data, how to create a competitive advantage using IoT analytics, real-life open source projects, Edge X Foundry, and new real-time critical edge compute blueprint. It has always been interesting to see how others have done it. Now, our first session is entitled Open Source for the Fourth Industrial Revolution, and our speaker is Shane Dewing, Senior Director, Software Strategy and Open Source in the Industrial Solutions Division of the Internet of Things Group at Intel Corporation. Shane is a veteran software developer and technologist and a pragmatic proponent of open source software. He's currently a project technical lead at the Akrano Edge Stack project in the Linux Foundation and previously served as a working group chair in the All Seen Alliance in the All Join open source project. Shane also works in IoT and industrial standards, including the Open Source Process Forum, Automation Forum, the OPC Foundation, and the Open Connectivity Foundation, where he chaired the industrial TG 2015 to 2017. Shane, welcome. The floor is yours.
Thanks, Greg. Good morning, good evening to everyone around the world. Thanks for joining today. Again, my name is Shane Dewing, and I work at Intel in the Industrial Solutions Division. Obviously, the industrial IoT is a very broad category, and in the Industrial Solutions Division at Intel, we focus on a few verticals, and the one I'm going to talk most about today is manufacturing, and in particular to Greg's opening, what trends we are noticing happening, particularly in manufacturing, that are leading us to look at open source as solution vectors as we move through this evolution of manufacturing at the industrial edge. So let me. Okay, so we've been marching along since the mid 1700s, harnessing initially energy, different forms of energy to help essentially with automation. So in the 1760s, we started harnessing coal and steam, and that, generated the initial automation around, transportation and farming. And that moved, generally, again, around 100 years, we saw, the harnessing of electrical energy. And obviously that was, a lot more automation started happening in factories. We started seeing production lines come around. And again, things have moved generally in these 100-year segments to, the mid-1900s, 1960, 1970, where we started, essentially not so much harnessing electricity, but now leveraging electricity in different format. And in this case, it was, in silicon, the production of silicon chips and electronic communications, which really is still the revolution that we're riding, that wave that we're riding now. Obviously, Moore's law has helped us a lot in terms of, getting more out of our compute devices, more transistors on a chip every 2 years, leading to great economic value out of the silicon itself. And this trend has continued, and especially in manufacturing, we've noticed, over the last, probably 10 to 15 years, tremendous progress in automation at the industrial edge. In the sense, what's happened is we're actually leading to what we now call that next industrial revolution, the fourth industrial revolution, which really is going to be highlighted by this complete fusion of the physical and digital world. So today we still have a high separation between physical. You've got a machine, it's got sensors and actuators. Some of them might be digital. A lot of them are still very analog by nature. And then sitting somewhere behind the machine or attached to the machine is you have a controller, which essentially is, connected either, digitally or via analog to the sensors and actuators. And the controller is running a computer program that is controlling the machine. As we get closer into the revolution, this fourth industrial revolution, that entire system is going to fuse into one, where the compute itself, the applications that control the sensors and actuators will become part of the machine. And we'll see, very little separation between physical and digital. We're marching towards that now. We're not quite there yet. At least our predictions, we're not quite there yet, but we are heading in that direction. And it's a very interesting trend for us to watch, especially from an open source perspective. once we, if we look, more closely at what this fourth industrial revolution really means, a couple of key attributes come out from systems that are going to operate within this paradigm. First of all, fully software-defined infrastructures at the industrial edge. Again, today we tend to have the separation of physical and digital, and in most cases, the control elements around machines are very vertically integrated. They can do one task and one task only. They generally marry the hardware part of it, the application processor, with the software layer, and that entire stack, that entire device is designed to do one thing and one thing only. As we move closer into this fourth industrial revolution, we'll notice that most of the elements of the machine will become software defined. Now, this is a trend we've noticed before in other revolutions that have happened. For those of us that have been around networking for the last 20 or 30 years, will know that in the last 15 years or so, a big revolution in networking happened where fixed function networking devices like firewalls and switches, for the most part, have now become software defined. And now we have, a spread of networking around the world where, elements of the network can be controlled from anywhere, essentially, through the software definition. Same type of paradigm is coming now down to the industrial edge. Multi-way communication. Machines, that have, basically from the 60s all the way through now, have developed around a multitude of protocols that they speak, to connect to each other. Most of these are highly proprietary and non-interoperable. As we head into this revolution, again, once we software define all these elements, the notion of interconnectivity between the machines and between the processes in the machines themselves will become, commonplace. So multi-way communication. The use of machine learning and especially training, within the machine itself is going to become paramount. It can be a key tenet of this industrial revolution. So, so leveraging the data produced by machines to train the machines in terms of re-optimization or even alternate tasks. End-to-end security. I think everyone's aware of the risks of IoT and the risks of bringing software definition into control systems, and so security is going to be a huge tenet throughout this revolution, starting in the physical hardware itself and moving all the way through that software stack, and then finally again the industrial revolution will take advantage of what's already happened in networking. So software-defined networking will also be a key tenet, we believe, of this industrial revolution. The good news from an open source perspective, or at least from a software perspective, is most of these processes that I've listed here already are operational in other industries and can be highly leveraged into industrial manufacturing. So what are we seeing as leading indicators that that we're using to gauge where we are in this transformation? So the first is some new standards work that is happening. So the Open Process Automation Forum runs under the Open Group, and it is basically the entire value chain in industrial manufacturing is participant in this to produce a new standard of standards. In other words, modernize the standards around industrial manufacturing. And address some of the key pain points that have been brought in primarily by end users, but pretty much across the value chain. So interoperability is a big driver in this new OPAF standard. Portability of applications and services, again, breaking the application away from the underlying hardware. So you can now have potentially a device from one industrial OEM running an application from some other OEM. And then finally, and this is really a big driver from end users, is sustainable software that drives down operational costs. And again, all of these, these key drivers in this new open process automation standard are very well suited to open source. So a little more in terms of, what's happening at the industrial edge. So most manufacturing systems follow what is called the ISO 95 standard. The ISO 95 standard, details different layers within the manufacturing environment where different functions exist. And then it defines, how these functions will communicate with each other, what type of interfaces might exist between them. But clearly these layers are quite hard to find. And so, right down, at the physical layer, at the process layer, I don't list them all over here. We've got a layer 0, which is the process itself. But around layer 1 is where the actual controllers and supporting functions for the controllers exist. You may have a data historian there. Layer 2 has already been more of more broadly control across your entire factory. Here's where you find your SCADA, maybe some HMIs. Certainly your MES would live in this layer. And then as you build up the layers, you get more into into the enterprise layers and more IT type of infrastructure from a software perspective. Generally, layer 3, down to layer 1 are considered operational technology or OT infrastructure. And for the most part, again, these software infrastructures have been very, or at least today are for the most part, vertically integrated. They are single function software stacks that run for the most part on single function devices. So this is now evolving, and this is where the Open Process Automation Forum is headed from a standardization perspective, is they're looking to collapse a lot of these traditional ISO 95 layers and bring the notion of, the capability at least of running multiple functions on single compute devices. So this is we use the word workload consolidation. It's consolidating existing workloads onto general purpose compute for the most part. It's also bringing in a new networking paradigm. So you'll notice we list over here Ethernet TSN. So TSN is an IEEE standard for time-sensitive networking, basically deterministic networking using traditional TCP IP methods. And again, we see this type of networking flowing throughout the factory, so that you have time-sensitive and deterministic networking where you can move data from a controller to a machine, from the machine, into an insight platform. So you could maybe run a machine learning algorithm, derive some insight, and have that insight flow again in a deterministic, time-critical fashion back to a controller and potentially back to the machine. So this flow of information throughout the factory now, getting rid of a lot of these hard-coded layers in the ISO 95 stack is really where it's headed. And again, we'll show, this idea of being able to move data and communicate throughout your factory, seamlessly is a key tenet again of where this is going. Behind all of this again is the software definition of all of these fixed function devices. So, what today is an HMI might be a hard-coded device. It's, it's a screen, that shows some information about your factory. Tomorrow, it's just a software workload that can run essentially on any device, and you can move it around. You can basically take that HMI and place it where you need it. So another big driver we see happening as a result of this revolution is the need for edge compute. So I think everyone's heard of this whole big push towards edge compute. We see it as an output of this industrial revolution. So as more of these devices at the edge become software defined, what really happens is you start unlocking the data that these devices produce. You put it onto time-critical networks, time-sensitive networks, and now you have this, immense amount of data being produced at the edge. And, while traditional IT infrastructures generally live in data centers, and for the most part of the last 10 years have transitioned to the cloud, we see that as we unlock more of this data at the industrial edge, that the data will actually stay there. It'll be, produced, analyzed, and stored at the edge. And to do that, this whole idea of edge compute is becoming more of a reality. And if you look at some of the data that's going to be produced, we anticipate, a smart factory is in the order of a petabyte of data a day. So even with the advent of, very high bandwidth networks like 5G coming along, there is just not going to be enough bandwidth to move all of this data from the factory floor through the enterprise data center into the cloud for processing, and then all the way back again, to affect a control system. So we believe for a lot of these devices, and for the most part, even in factories and other, edge processing environments, the data will remain there. So this is another big trend that we're noticing. And again, the core value proposition behind this from an open source perspective is to manage this amount of data, you need the types of IT infrastructures that already have been developed for enterprise and cloud. And again, most of these today are open source. So taking all of that, what I've done here is I've looked, across the landscape of open source, and I'm going to pull out for you guys just a few of the key projects that we believe are going to help drive this industrial revolution, and more importantly, the whole move to edge compute. So I've called it the edge compute landscape. Some of these projects I listed over here are very industrial specific, and some of them are very IT centric. Again, this whole industrial revolution is going to marry the two together. So just to quickly reference the green boxes, denote the very large open governance foundations for open source. So OpenStack Foundation, Linux Foundation, Eclipse Foundation are the big notable ones. The orange dotted boxes are, single company funded open source projects. So, generally speaking, closed governance, but still, open by nature. And then the black boxes denote, umbrella projects within the big foundations. So I'm going to run through just a few of these for you. I'm not going to touch on every project. I'm going to call out just what I believe to be the more important ones. And we can deal with the others in Q&A later. So starting at OpenStack Foundation, there are a couple of projects here that we think are highly relevant. Again, OpenStack, for those of you that are not familiar with it, is really, IT-centric infrastructure for managing virtualization, hardware virtualization at scale. So a lot of cloud service providers use this, a lot of telcos use OpenStack. There are two projects at the OpenStack Foundation we think are very relevant for industrial computing and especially edge computing. The first is Starling X, and the second is the Kata Container project. Starling X is really a highly available instance of OpenStack, along with a whole bunch of networking abstraction layers as well. And it also brings in this notion of a single pane of glass. So you can manage all of your infrastructure at the edge using a single manageability UI. So both virtual machines and containers can be managed in that way. So highly relevant. Another key tenet of Starling X that we think is important is, even though it's IT based and is, it comes, primarily from cloud infrastructures, it can scale down to a single node. So you can bring it onto the factory floor and run a highly available IT-based infrastructure, virtual machines, containers, network abstraction layers, all in a single node. Kata containers, very interesting in that, one of the problem statements of software defining certain control layers at the industrial edge is this notion of time criticality or deterministic compute. Containers by nature, especially Dockers, have not been built with time criticality in mind. Kata containers are really virtual machines. They can take advantage of hardware-based acceleration, but they manage themselves like containers. So you manage them through a regular container infrastructure, but they can take some advantage of hardware acceleration to get more closer to that deterministic nature that you need at the industrial edge. So those are two at OpenStack Foundation that we think are highly relevant. Moving on to Linux Foundation, I've called out a few here that are, very IT centric that we know are, these infrastructures are now starting to come, down to the industrial edge. Big focus around the Cloud Native Computing Foundation. This is where Kubernetes project lives. Kubernetes is, essentially a container management framework where you can manage, moving your containers from cloud to edge and from edge to edge infrastructures. It also contains the OCI, Open Container Initiative, and this is where the Docker project lives. So these two work very, very closely together. And then we also see, quite a bit of interest in the Cloud Foundry. So Cloud Foundry, again, is more of that application enablement layer that can sit on top of these cloud native type of infrastructures like Kubernetes and Dockers. So those are highly relevant. On the networking side, these are existing projects that, that kind of sort of carried the whole telco and service provider industries into the software-defined networking realm. We see them again as highly relevant for industrial. So you've got your LF networking, LFN, that's basically where you have your software-defined networking, the automation of your networking functions. In the ONAP project, we see DPDK as a highly relevant. Again, this is packet acceleration, basically bypassing the Linux kernel, so you can get fast movement of data from your network interface directly to your application layer. And then the soft switch capabilities that OVS brings. So the capability then of having a software-defined networking environment, basically operating at the lower layer of your compute device or your compute stack. So we do see networking as highly relevant. Again, these are existing projects that are retooling for some of the intricacies at the industrial edge, especially some of the different protocols that might exist down there. The new one that I want to talk about a little bit is Linux Foundation Edge. So Aleph Edge is a new umbrella project created by Linux Foundation to focus on edge compute. And there are a few projects here that really focus, again, down at that industrial edge. The first being EdgeX Foundry. So this is really for ingesting the data. So it's data discovery, data ingestion, data tagging for analytics and machine learning, data storage, data publishing. So everything around data, data management, EdgeX Foundry is doing that. They have a cloud native compatible environment, so everything's containerized, so you can move these containers onto compute devices in the cloud, in your enterprise data center, maybe a data center at the industrial edge, and always and even down at the control layer. You can run these containers. So a highly relevant project. It's gone, I think it's now in its third or fourth public release, so quite mature as well. The other one I'll call it here is the Acrano Edge Stack project. This is a unique project in that it's blueprint based. So no code contributions generally within these blueprints. The blueprints are more geared towards fast adoption of open source. And the way they do it is to have these blueprints, pull from other open source projects, existing open source projects, in a particular configuration for a set of particular use cases. And then in the blueprint themselves, they'll marry that onto commercial hardware and validate that software stack from the various upstreams on the commercial hardware. And then, that particular version of the blueprint can be picked up and leveraged directly into production. So it's a way to speed open source, into production. And from an industrial perspective, Intel, my company, is invested in what we call the time-critical edge compute blueprint there, that is pointing to a couple of different upstreams that we believe are highly relevant for doing real-time deterministic control in a software-defined way. Moving on. Acorn and Zephyr. So Acorn is a very lightweight, IoT-centric, real-time Type 1 hypervisor. So this is a hypervisor that runs directly on the processor itself. So it's not embedded within the operating system. Most of the devices down at the industrial edge will still, for the most part, they won't run a full-blown Linux. They might still run a real-time operating system. And so having the capability then to have a Type 1 hypervisor is really important. The combination of Acorn and Zephyr is a corresponding real-time operating system. Both of these in the open source are headed towards safety certification. So if, for safety critical types of applications at the industrial edge, where today, you mostly have to go to proprietary solutions, these two projects are offering similar capabilities directly in the open source. Switching across quickly to the far left, I've called out some of these single company funded or single non-open governance projects. Most important ones here from an industrial perspective we see is this Open 62541. So IEC 62541 is the standard, the IEC standard behind the OPC-UA specification. OPC-UA is a communication framework that allows for machine-to-machine and machine-to-cloud communication at the industrial edge. And this particular project is modernizing that framework to support a publish and subscribe paradigm, as well as support for the underlying IEEE TSN, Ethernet TSN networking. So very important. And then also, I know Chris is going to talk a little bit later around Influx, but Influx does have a very large open source footprint around their time series database and tooling. So those are very important. There are a couple of others here you guys can look up later. And then finally, we ourselves, Intel, we do our own open source, and we have an edge deep learning and inferencing toolkit that we call OpenVINO. And again, as we head into this fourth industrial revolution, where machines themselves will be able to, learn from the data they're producing, and essentially, re-optimize themselves, we believe that this toolkit is highly relevant. And then just very quickly, I want to talk through, how we see these software stacks at the edge evolving. So I've laid out a couple of, kind of sort of deployment zones at the industrial edge, and I've mapped in where today you would see the current ISO 95 layers. So starting, within the enterprise is what we call ISO 95 layer 3 or layer 4. You can see latencies here are generally pretty high. This is your traditional infrastructure as a service layer. So the types of software frameworks we see here are primarily abstracting hardware and providing, services around that abstraction. So, abstracting away compute, network, and storage, and providing infrastructure as a service capabilities. This is where we see a lot of CSP type infrastructure, whether it's Azure or AWS. A little further down to the industrial edge, we see this new kind of deployment zone called private cloud servers. Again, this is part of this industrial revolution, is bringing IT infrastructure onto the factory floor. This is an area where that Starling X stack would be highly relevant. And here's where we're noticing not only infrastructure as a service capabilities, but also platform as a service. So a lot more middleware is arriving in these software stacks, middleware like EdgeX Foundry, for instance, that is enabling this idea of, data as a service, and platform as a service capabilities. And then finally, right down at the very edge, again, by software defining these control layers, we are now seeing the notion of control as a service. Again, control used to be very fixed function point devices. Being able to expose that in a service layer now is what we see as a trend. So I'll move through the animation pretty quickly. Again, infrastructure as a service, moving more down towards the industrial edge. Platform as a service, we see creeping more towards the traditional enterprise. So again, moving especially data type of middlewares more, towards enterprise and especially toward the cloud. And then finally, we see CSPs, trying to bring their infrastructures closer down to where the data is being produced. So, right down into the industrial edge. And then finally, I'll just layer these, the couple of projects that I mentioned, so you can kind of see where they fall in these different deployment scenarios down at the industrial edge. So Crano, again, blueprint driven, they'll have blueprints across all these different layers that'll look at all these different infrastructures, both platform and infrastructure. EdgeX Foundry, very middleware centric, so much more around the platform as a service capabilities. And then finally, I'll call that Starling X again, very IT type centric in terms of the software layers it produces, but can scale all the way down to single nodes, so very well suited for that private edge cloud server. So I think that was the end of what I want to cover in my section.
Fantastic. Thank you, Shane. It's always staggering to me when you look at these types of applications. I mean, the volume of data we're talking about, it's almost incomprehensible. I mean, 1 petabyte a day from a typical factory. It's hard to put that into perspective, but I'm sure we can Google something and find some reference points. So our second session today is presented by Chris Cirillo. It's entitled Why Open Source for Time Series. Now, Chris is responsible for product marketing in Influx Data. Prior to joining Influx Data, she defined and designed a SaaS monitoring solution at Centroid, and prior to that, she was the Vice President of Product Management at iPass and held responsibility for line of business for several cloud services that required her to track the business and operational metrics and analytics to help identify and resolve issues. So thank you for joining us today, Chris. The floor is yours. Excellent. Let's move to the next slide.
And so why time series? So why are we here so specifically? We got a really great overview from Shane, and there are so many different components that you guys have to think about when you're in the industrial IoT context. And, looking at that one chart that he had, time series was just tiny little, or InfluxDB was this tiny little square on the left-hand side. But really what we actually manage is time series data. And if you think about what your sensor data is, or all the data that's, coming from all the machines on the factory floor, the subunits on there, sensors that are on there, the additional sensors that you might put on there. If you think about what's actually getting produced from a data perspective, it's all timestamp data. It's a value or a set of values, maybe a set of meta information, and then there's always a timestamp. And then the reason is that what we're really trying to accomplish with this data that we're collecting is we're trying to understand what's the performance like. Are things going up? Are things going well? Are things not going well? Is there a chance that we can have even more production in our factory floor? Is there a chance that something's going to break? All this data is trying to help to inform us to understand what's going to happen and how we can take advantage of that information so that we can kind of be ahead of the game. And this is all time series data. This is all trying to understand change over time. Next slide, please. So we actually, we see a lot of different kinds of time series data. We see time series data that's getting collected on almost all, well, definitely all the different layers that Shane talked about, at the network layer, at the application layer, the physical, the virtual. We heavily have been involved in Kubernetes and containers, all kinds of different standards. And really everything that you saw in that chart that he had actually requires some form of monitoring, because we want to make sure that those things are going to be running effectively. We want to make sure that your networks can handle the data that's getting pumped through there. You want to be able to make sure that your application is actually running as you expect it. You also want to be able to understand, if the users are actually on certain pages and they're clicking on certain buttons, that the response rate is actually something that a human can tolerate, so that they don't feel like something's broken. Everything that we have to pull together requires some kind of monitoring. And so it requires some kind of metric and event, and essentially time series data. But what's interesting is when you start to dig into the kind of data that we're actually needing to pull for these systems, they have some characteristics that make them very, very different, even though they are all time-stamped and they have this value. And so I just have this comparison here of what I call your typical DevOps kind of metrics. So this is trying to understand CPU load, how much server is being used, how much disk space is being used. And, typically what we need to be able to collect data from that metric perspective is that we need to have resolutions between the seconds, maybe the minutes is tolerable. And the retention of that data is actually surprisingly, pretty short. Whenever you are trying to track to see if the network is performing, you really want to know the now as much as possible, so that then you can try to, see if there's something that I have to address really quickly, get through the resolution and go. And so that means that in this moment, in real time, I need to collect a ton of that data, as much as I can. But then over time, what's really interesting with this DevOps kind of data set is that you actually don't need that precision. And so a lot of times that data then gets downsampled or aggregated. And because you only need that aggregated data for reference, for forecasting, for historical purposes, but you don't need all the nitty-gritty details. You just basically need kind of the shape of the data to understand what actually happened with that CPU load. And you can see here the goals here are really about performance monitoring, incident management and detection, so that we can get to resolution really quickly. What's different in the IoT world is, of course, you will have the systems that you want to monitor on the DevOps side, but you also have a lot of different time series data that you're collecting that's really relevant to the machine or the process, that you have within the in the factory floor. And so we're looking at metrics that are more like, temperature or pressure, valve state. Is it on? Is it off? Rates, is the water pumping from this one, tank pumping at a certain rate, and is it going to? You need to understand, is that tank going to get filled up, and is the previous tank going to get emptied out too quickly? totally different kinds of metrics that we're looking at. And in some instances, especially when we're looking at metrics for things like pressure, that resolution of data needs to get into the subseconds, because you just can't see any noticeable change that's going to invoke the need to, understand if this is a problem, and then try to take care of it. Now, the retention on this data is, well, there's no downsampling. You definitely want to be able to keep that data and all the data for forever, at least 5 to 10 years. But if you could, you'd want to be able to try to take it to infinity, because this data is really useful in helping you to achieve those production goals that you have, also help to elevate the quality. And in some cases, I've actually seen some customers that have been able to use some of this metric data to prove the quality of the product to their customers, and actually use it as a differentiator for themselves. But all that meant that they had to have, different kinds of data, and they had to have lots of it, and they have to keep it forever. Oh, and then, I think the other key thing that we have to remember is, if you want to do like real predictions, especially if you want to throw this data into any kind of machine learning framework, you need to have a lot of data. If you have just a little bit of data, you're not going to learn anything. There's not going to be anything interesting about what's going to get trained. All that data that you throw into those models, if there's very little data, it's not going to tell you anything. And you can simply just test this on yourself with something simple as weather data, right? If you know that you only have 6 weeks worth of weather data, what are you really going to be able to predict, right? And so these weather models that we always see the meteorologists talk about on television, they have a ton of data. They have data coming from all points of the world for hundreds of years, and they are collecting it and then really constantly refining their models. So you need a lot of data to be able to make some really great predictions with ML. It's definitely possible, but you just need to make sure that you have to keep that in mind, that that data is required. Next, please. So, some of the challenges that I think are a little bit different from a DevOps perspective in regards to this data is that, and Shane really touched upon it, is that, of course, there's the scale, the speed, but we also have to consider that, storage. If we're going to keep all this data around forever, you're going to have to really consider, where you're going to store this. Also, distribution and even the processing, where you're going to be processing this data. Really need to, think about what kind of impact this is going to have on your architecture. And Shane kind of talked about, if you're going to be pumping all this data from the edge and trying to get it to, some central cloud, you're going to have some pretty big fat pipes that are going to have to allow you to be able to do that. And so all these things are, pretty big challenges that you guys are faced with in order to be able to get to this new world of being able to, look at data in real time and make some pretty quick adjustments that are going to have some big impacts on your production and your top and bottom line. So what that means is, we really need to make sure that, yes, there are a lot of cool tools that you can use, but we have to constantly also think about, are these things going to be flexible enough and open enough for me so that, one, I can, as I migrate into some of these new technologies, we can't lose the fact that, these systems that you currently have to still be supported, right? These legacy systems, they don't just disappear overnight. So you need to make sure that these systems can be able to handle what you currently have, pulling data from those things, and then also pulling data and being able to harness that data with some of these more kind of modern technologies. We also need to make sure that the demand for these new storage and processing capabilities isn't just going to be one way. It's got to be multiple different ways to be able to help to accommodate the transition that you're going to be making. And then over time, you may even learn that the way that you thought you were going to be processing this data, maybe it wasn't as efficient yet as you hoped. And so you want to be able to have that flexibility to even, anticipate that even, more architectural change might be required. So it's a lot of things to think about. It feels a little bit overwhelming. But the good thing is there's been a lot of people and a lot of organizations that actually have looked at these things and actually have come up with some solutions with some really great open source projects. Next slide, please. So in my world, I just look at the IoT platform very simply. So this is actually not too different than what Shane showed us. So, I usually see a lot of these different providers that are going to, be touting that, oh yes, you have to have, just compute at the edge or in the cloud. But to me, it's really just separated by the edge and then what I just call a hub. And the hub is just basically where maybe where you're going to store a lot of stuff and where maybe some of your enterprise applications going to be living in. Can you do the next transition, please? And so on top of this is that what I typically see is that there are actually 4 different kinds of services that actually live across these various types of architectures that various players in the market are currently working on and selling to a number of you guys. But what I think is important to understand is that there's a data services layer, which I'm going to go into more detail. But there's also a security layer that you have to think about, making sure that security is understood and taken care of all the way from the edge to the cloud and the enterprise applications that you guys are building. Of course, there's device management. There's always been device management in IT. There's even more with the factory floor. And then even when you have these subunits and also these sensors that are way, way, way out in the edge, everything needs to be managed because you want to make sure that, that of course, where, all of your, all of these devices are. You also need it from a security perspective to be able to understand, okay, what has been patched, what hasn't. But also this device information actually provides a lot of really great context to the data that you're going to be collecting. And then there's also this connectivity layer, which is going to be varied depending on where your solution is. If you are in a hydroelectric plant and you're way, way deep into the plant, you might not have any kind of, connectivity with the outside world. So you have to rely on things like LoRa, or maybe you have to build out your own networks. If you're in a really, the urban area, you don't have that problem at all, but it's always going to be top of mind because it's not going to be consistent and it's going to have lots of different requirements. So let's dig into data services just a little bit more since I kind of skipped that. So let's go to the next transition. So this was actually some data that was collected by the Eclipse Foundation. And so when they conducted a survey to understand, what is this data? Because we're always throwing all these big numbers at everybody. And they really dug into to try to understand what is the data that we're actually collecting and what is it that's going to, and I think understanding what that data is going to help us all, be able to be a little bit more informed and start to think about it in context with the architectures that we're building. And so 62% of the data that we're actually collecting is time series data. Is that data that I talked about, that value and a timestamp. Next slide, please. And what is important to note about this kind of specific time series data is that you have to collect it, right, from whatever sensor or whatever device that you have out there. In some cases, you want to be able to stream that in and start to actually do some analytics on it as it's being streamed in. You may then want to store that, enriched data or that manipulated data. You also may want to store the raw format of it. But then the next step that you need to do is then you need to often provide some kind of visualization to the management team, to supervisors, to the individual operators of these different machines so that they can, take control of, the areas that they're responsible for. And I have some really specific examples of that in the next couple of slides. So, so why am I talking about time series databases and what is a time series database anyways? Well, it's a specific type of database that's going to be able to handle the high ingest of time series data. Also, as you're having all this data coming in, you also have to be able to handle a high query, because as we start to look at the data, or as we start to collect the data, we're going to want to look at that data right away. And so, of course, you can use any data store that's out there. And most of the users that I've talked to and that I've worked with, we've all used some form of a traditional database. In fact, I would argue that most people actually start with a spreadsheet, and I think spreadsheets are still super, super common in the factory floor. And you can definitely use that for time series data, but you'll quickly find that it's very limited. And so then you might look around and go, hey, I've got my SQL lying around, I'll just throw this data in there and off I go. But the problem with that is that there's going to be a lot of work that you're going to have to do in order to make it work for time series data. You're going to have to index it for time. I've already talked about the query and the ingest issue that you're going to have to work with. You're going to have to also deal with storage. You're also going to have to, figure out, okay, how can I actually do some of that analytics or manipulation of that data? I want to aggregate it. Do I want to apply certain functions on it? Do I want to downsample it? All those kinds of capabilities you're going to have to build yourself if you're going to be using something other than a time series database. And so you might then start to look at other types of databases that are out there. You might think, okay, well, if the volumes are so large, then why don't I go and use something like a search database or, a Hadoop, a big data kind of a solution. But you're going to run into the same issue of there's going to be quite a bit of work for you have to do to be able to handle this kind of data. And, if InfluxDB is not the only time series database that's out there. The good thing is there's a lot of open source time series databases that are out there that you can take a look at. And you can try them all because it's open source, and you can see which one is really going to fit with your solution. But I do think it's important, whatever you do, that you really consider using a time series database, because if you think back to what Shane was showing you, there's a lot of other stuff that you need to be working on. And the last thing you need to do is just rebuild something that's already available that works very well with a lot of industrial organizations. Next slide, please. So specifically about InfluxDB, Influx Data is basically the company that's behind these 4 open source projects, and you might have heard of InfluxDB, and this is the time series database. We also have Telegraph, Chronograph, and Capacitor. Telegraph is actually probably for me the most exciting open source project because it's basically a collector agent. And we've only written about 10 of these collector agents, and there are 220 currently available. And this really shows the power of open source. The rest of those 210 Telegraph plugins were actually written by the community. And so, somebody in the community is trying to build a solution. They have a particular data set that they're trying to bring into a time series database. And they just build this plugin and they just make it available to everybody. So then the next person who needs it, they're like, cool, it's already there. And in some cases, I've actually seen community members that have made a request saying, hey, I'm not comfortable building this. Can you help me? The community, more often than that, will actually respond. So just in the span of a couple of years, a lot of these plugins have come into play, and they're completely open. You don't have to use it with InfluxDB. You can pull the data with Telegraph and throw it into a different time series database if you want to. And I think it's really important. And you might think I'm a little bit crazy because you're like, hey, you probably want everything in InfluxDB. But the truth is, closed systems are not useful to anybody, right? There's things just change over time. And we need to make sure that we make all these systems very open, very simple for people to use. And then it's up to, organizations like ours to make sure that, hey, let's make InfluxDB or the projects that we're working on really solid and really appealing so that people will choose to use these things, not just forcing people to use it because it's closed and just this is the only way to do it. So it just puts more pressure on us, but I think it's going to be better for everybody in the long term. I'm not going to go through all the bullet points on the bottom. I think I've covered them in just the other slides that we're talking about it, but I wanted to show you on the right hand side, what time series data looks like in the context of InfluxDB. And when you look at some of the other time series database, they have a similar type of a format where you have a measurement name. In this particular case, I gave it a really boring measurement name of telemetry. But there might be metadata that is interesting to me. So you can see a product ID, battery type. Those are, information that I might want to be able to group this data by. I might want to be able to see, okay, all the lead acid type of batteries that are, product ID 1, 2, and 3. I want to see, how well they're performing out in the field, and then make some kind of adjustments. And then you can see voltage, current, and temperature. Those are those values that I talked about. And you don't have to, just have one value. You can have multiple values that are attached to this particular measurement. And then we have our timestamp, and the timestamp, can go from an hour to a minute, all the way down to a nanosecond, depending on the type of data. And you wouldn't apply, the same rules to all the data, all the time series data that you're collecting. They're all going to have some variances. And so you want to make sure that the solutions that you choose allow you to handle those variances with no engineering, basically. You want it to be something as simple as just a configuration setting. Next slide, please. And I'm now going to just kind of go through very quickly a couple of different use cases. But if you look at my very, very simple view of the industrial IoT world, you know, the data that's coming from all these, you know, basically edge devices, if you think about it, are time series. A lot of it is going to be time series data. And we have a lot of different users that have come up with a lot of different architectures. In this particular case, we have a lot of users that are using OPC-UA as a mechanism to get that time series data into InfluxDB. But that's not the only way. There's MQTT, a bunch of pub/sub type of mechanisms to get this time series data into InfluxDB. There's also something called DDS that, that some of our users have used. And the nice thing is these mechanisms for bringing that data into InfluxDB have been already open sourced. So you can actually start to take advantage of that really quickly and start to look at that this data and not feel that you have to you know, continue to use your existing solutions. Next slide, please. So I'm just going to talk really briefly about a couple of these use cases. So this is a use case of a energy producer in Europe, and you know they knew that the management team knew that there was a lot of waste. They just didn't know where, and they also knew that you know the teams underneath were doing the best that they could. It wasn't that they were intentionally being wasteful. They just knew, they had some intuition that they needed to have some data to help them understand what was actually going on. And so what they started to first do was just collecting all this data centrally. They had an old data historian. It didn't really give them the ability to have a centralized view. A lot of data had to get stored, you know, in a closet. They used to have to take a hard drive, bring this to the closet, grab the data to even just look at 3 months worth of data. And then what started happening, which I hear more and more and more at these factories, is that then someone decides, oh, I'm just going to take a little bit of this data, I'm going to throw it into Excel, and then I'm going to do some manipulations, and then we're going to base our entire year of production on this one moment in time snapshot. So they knew this was not the right way to do this. And so what one of our users was able to do is they actually built a much more modern data historian, actually using a lot of the components that Shane actually talked about. So a lot of containers and orchestrators, a lot of more virtualized networks, et cetera. But what they also were able to do is collect all the data from all the components in the factory floor. And for the first time, the management team was able to see all this data in just a centralized view. So now they had these dashboards. And then in this particular case, they were using Grafana dashboards, which is another really cool open source project. And they could start to see, you know, what all this data that they were collecting on the factory floor actually looked like. And then, you know, over time, they started to realize that they could, you know, start to transform this data by, you know, enriching it with other kinds of time series data like, you know, weather forecast information, customer demand information. And so they started to find places that they could be a lot more efficient. But the place that surprised them the most is they just realized, well, this is open source. Why don't we just let everybody in the organization have access, you know, to these dashboards? And so the operators themselves weren't just looking, you know, at the machines that they're responsible for. All of a sudden, they now had access to the data, you know, end to end, you know, from their production facilities. And a couple of guys started just poking around, just looking at these dashboards, changing the queries a little bit. These guys are not programmers by any means, right? But they just had this curiosity about the data. For the first time, they could see this data in front of them. And it turned out a lot of their day-to-day workings was based on, you know, things that they had just learned over time. But this gave them a different perspective of being able to see, you know, data that they never even saw. Maybe they never saw that the HVAC data was, you know, looking like this. And then they started to realize this could actually have an impact on, you know, what I'm working on over here. So at the end of the event, a couple of guys were starting to poke around with this, and they saw something funny in one of the tanks, and it turned out to be a leak. And it was really, really early that they were able to catch this leak, and they were able to address that very quickly. ended up saving them about $500,000. And it's not a case that the management team expected. They never thought that giving data and giving these more modern tools to everybody in the organization could actually have some pretty, significant impacts. So I'm not going to go over the rest of the use cases. There's a ton out there. You just can Google, time series and industrial or factories, or even InfluxDB. And a lot of these use cases, you'll definitely hear a lot about how people were able to really take advantage of the data that they're collecting and do something quite significant. But the number one step is you got to start to collect it. You got to figure out where you want to do the collection and where you want to do that processing. So we're almost at the top of the hour, so I think I will stop here.
Wow, thank you, Chris. That was definitely a lot of intense material that, my gosh, cutting edge. You look at all the implications that are available out there for just this type of real-time monitoring and the volumes of data that are generated. It's staggering. But now we've got a bunch of questions in the queue, so it's time to transition to our Q&A portion of today's session so we can entertain some of these. Now, several of you are asking about the content from today's session, and I can answer yes, the presentations will be made available after the conclusion of the conference, so no need to worry there, and we'll be carrying over the conversation to Twitter as well. Which brings me to a second point. We have two options for submitting questions today. You can use the Zoom Q&A tool, which most of you figured out, I can tell by the volume coming in. And you can also send in questions via Twitter using the hashtag IIoTAI. Once again, that's hashtag IIoTAI. And if I can't ask you, please don't submit questions through the chat window because these won't be incorporated into the Q&A. So without further ado, let's dive into some of these. Maybe we'll kick it off. A bunch of questions came in around just a general concept. So Shane, I'm going to direct this one to you. Today, open source software is not very well leveraged in the industrial operational technology deployments or OT space. Now, from your perspective, what's changing in the ecosystem that would make open source more viable for future OT deployments?
Well, great. That's a great question. So I think, as I ran through my presentation, I think I listed out, a couple of trends that are relevant here. So the first again is, this move to software defining, the actual workloads that run at the industrial edge. And if you start software defining workloads, you need infrastructure for them to run in. So this infrastructure might be a virtualization manager. It might be if you're going to use containers, to manage your software, maybe it's a container manager, and there's probably a bunch of additional infrastructure, system management infrastructure. So really this infrastructure software, we believe that, it's been developed over the last, 20, 30 years in IT becomes much more relevant now at the industrial edge. There's been this gap, both in hard gap, we call it an air gap sometimes between your industrial, your OT network and your IT network. Machines don't really talk to each other. Lots of reasons for it. But as we start bridging this gap now and bringing IT infrastructures onto the factory floor, it's more of this infrastructure code that we think is mostly relevant, at the industrial edge. So that's where we think it'll start. The ecosystem is going to start rallying around this traditional IT type of infrastructure to bring down to their machines. And again, we see it primarily going to be in manageability. So manageability of your hardware, manageability of your software lifecycle management, those types of frameworks, which again have been, in open source for years, traditionally used in IT and cloud. That's where we see the transition happening.
Got it. So Nicholas kind of touches on this tangentially in one of his comments and questions. He says there seems to be a global consensus around the big data and big data lakes won't cut it, and that everything will be transformed into streaming data. Can you comment on that perspective? He goes on further to say, it seems like all the challenges discussed earlier with industrial IoT are being solved with EDA and stream processing technologies like Kafka, Lenses, Confluence, etc.
Is that for Chris, maybe?
Yeah, you care to take a stab at that, Chris?
Yeah. I mean, absolutely. Yeah. I mean, I think at the end of the day, like these IT systems have been, they've been successful. And I think, you know, the OT teams are looking at that thinking, oh my God, I think I need a little bit of that as well. But I think, you know, before you dive into, you know, trying to get into this whole world of streaming analytics and, you know, just dive headfirst into that, I think, you know, just start small, start on just a couple of smaller projects and don't go headfirst into like, you know, hardcore streaming. You know, just collect some of that data and start looking at it and start, you know, figuring out, just start doing some basic analysis of that stuff. Start to get really familiar with, you know, what can get pulled in. And then I think you start to think about, okay, now let's open up the faucet, if you will, and start to go hardcore. I think, you know, you want to be careful. You want to overwhelm yourselves, because I feel like a lot of us that have been using these things have been using this for a long time. We're very familiar with, you know, the things that you have to be careful with. It's really cool. It's really great. But definitely I have, you know, my own scars from doing things the wrong way.
I can imagine. Audie has a question. Still thinking about how to take their projects to the next level. What is the way, or what's the best approach to choosing any of these open source IoT analytics platforms? So any insight into how to choose the best fit for an application?
You know, the cool thing about open source is that it's free, right? And so, and the other thing that's really, you guys are really fortunate about is that, you know, sensor data is available in your house. And so you could actually just over a weekend, just get started by downloading a couple of these open source projects. You know, look at the sensors that you have at your house, start to monitor temperature, start to monitor the temperature of the pool, the house. People have, you know, these barbecue probes. Start just kind of playing around with these different open source projects and get just familiar with it. It doesn't cost you anything but time. It's such a really nice way to be able to get started. And I guarantee you, after playing around with it just for a couple of hours, you'll have these amazing dashboards. You'll have done some amazing transformations on just some of the basic data around your house that'll then inspire you to, you know, think about what you could then do on the factory floor.
Yeah, and I'll just add to that, you know, again, you know, still today, the primary challenge for any analytic, you know, application that you want to deploy is getting access to all of the data.
Yeah.
And so, you know, there are a couple of open source projects that look at that specifically. So I'd mentioned EdgeX Foundry as one. You know, they've got this connector framework that, you know, that we can plug in industrial connectors and connectors for other sensor types, even potentially for smart home. But I think that those types of frameworks are probably where you want to start. In other words, how do I discover, onboard, ingest, and manipulate the data before I can even run an analytic function against it? I think that's still kind of one of the challenge areas, and that's probably where I would start, is looking at the open source projects. You know, Influx has them, and obviously we mentioned a few at Linux Foundation that allow you to discover and ingest the data. I think that's kind of the starting point from my perspective.
Yeah, I think you're absolutely right. And be careful asking the manufacturers of the equipment to help you with it. A lot of them still are not quite there yet. You know, they're just still in that, this is our data format, this is closed. So it's a little bit foreign for them. That we're starting to see them change a bit, but I think they're just not there. And so a number of these users that we have that are, you know, helping to modernize these factory floors do have to work really hard to get that data. It's not that, you know, all the machines and subunits have like one particular subunit. You know, these machines are from lots of different manufacturers. And just as Shane said, look at some of the open source contributions for collecting that data. There's a bunch of Pi connectors out there. There's a bunch of OPC UA connectors that are out there, all in GitHub. You just have to Google it and you'll see. It just all shows up. It's pretty cool.
So I had another question for you. This is something we haven't touched on yet in this one. It's probably a bit of a Pandora's box, but Subrata is asking, well, what are the possible data security risks and how do you deal with them? So maybe at a high level, without jumping into a second session here, any high level suggestions for cyber aspects of these with open source?
So I can start, and Chris, I'm sure you've
Yeah.
got some stuff you can layer over. So it is probably the biggest challenge right now is, as you piecemealing different, software frameworks together, is to maintain, a comprehensive security paradigm end to end. Coupled with that, a lot of the data producers themselves. So, if I come from a manufacturing perspective, a lot of the programmable logic controllers or other controllers down at the industrial edge, they are secure because they're not supposed to really be connected to an IT network, and so they don't have traditional IT security frameworks within them, and so the data they produce is inherently insecure, and so some of that data is going to be coming across an insecure link, and you're going to onboard and then try and add security later, and so it is a challenge. One of the things that the industry has rallied around, and this is, Intel was very good, and ARM, they got together last year, and they came up with what's called secure device onboarding, which is basically an immutable root of trust that's embedded in the CPU at manufacture time. And then, coupled with, cloud services, you'll be able to essentially onboard and then track the life cycle of a device, using the secure root of trust. But that same root of trust can now be used to secure data directly on that producer. And so this gives you a way to anchor your root of trust and then carry that same security framework, all the way through where you might eventually, store data in a cloud or even do some deep learning in a cloud. All of this now can be secured in a common way. So I think it's a great step in the right direction, but probably more work is required.
Yeah, and in the whole IT side of the world, there's been a lot, right? We have a bunch of open source tools where you can scan devices to see, what vulnerabilities are on there, patch them. There's a ton of, different SIMs that are out there. These are looking at event data. Event data in the security world is going to be, hey, did Shane log in, at 3 o'clock into this system, and was he allowed to? All that kind of information, already gets stored. There's a ton of tools that are out there that can help with that. So we could talk forever about security, but I think security, for me, it has to start from a cultural perspective. You can have all these tools that have all these wonderful secure options, but you really need to make sure that it really becomes a part of the company's culture. And so there's sometimes it's just as simple as just doing some trainings for people. I've gone through it. There's even software engineers get, trained on security. I think it has to be part of the DNA, and then you can start looking at, okay, what are the solutions that make sense, and how do we actually implement them? I mean, we all have to be cognizant of it. We can't just have this poor CISO sitting there, worried about it. Every single person that's in the chain, has to be a participant when it comes to security.
Well, I've got one final question, and then we'll break up because I want to be conscious of time. But there's some fantastic engagement going on here. Giovanni'd like to know, from your perspective, is it enough at the moment to manage all of this data, all this influx of information with artificial intelligence and machine learning, excuse me, or is you think the plan to go to more of a deep learning type of an approach? Any thoughts there?
I think this is a religious debate.
Fair enough.
Well, so I can give you our perspective on it. So when I showed that slide around what we believe to be the key attributes of the fourth industrial revolution, which is essentially fully automated systems. Obviously, the capability for the system to self-diagnose and correct operational parameters in real time is paramount. And so, doing machine learning and training of the algorithms directly in line with the data right down at the industrial edge, we absolutely believe is a trend that is coming. No doubt, at a factory level, at an enterprise level, trawling through all the data again and gaining additional insights that can come back and retrain algorithms will also occur. So we see both paradigms. So, the deep learning, kind of sort of the slower, non-real time trawling through your large data lakes and data pools, absolutely will sustain, but we do see this notion of bringing inline learning and training right down to the machine level.
Yeah, and I think, you know, what I see with a lot of our users out there is that it's also going to depend on what they're trying to do predictions on. You know, is it a bunch of electrical lines that they need to, you know, determine, okay, is this something that we have to send somebody out to do a truck roll to, you know, make some, you know, fixes? Is it, you know, something that is trying to understand, you know, this little widget that's controlling the number of the amount of ink that's getting pushed into an offset printer? You know, it's really going to depend on what kind of thing that we're trying to learn on, because sometimes it's going to require actually a lot of human conversations to help to contribute to, you know, the direction of the tools that you're going to use. It's definitely not going to be like this one size fits all. You're not going to just go, everything is going to be deep learning for every single thing. It's going to be, you know, dependent on the unit or the thing that you're trying to accomplish.
Well, thank you for taking the time to join us today. And thank you, Chris, Shane, fantastic engagement and insight into the realm of data analysis, manipulation, and ethereal management, if you will, processes at the industrial side. We've had a tremendous amount of engagement. Thank the audience once again for the questions that have come in. We'll be carrying this conversation over because we can't address the rest of these in the time allotted, but fear not, we're going to put out a special blog on this at IIoT World to address this. So stay tuned, and links will be forthcoming to that so we can carry on the conversation. Stay tuned for other educational webcasts brought to you by IIoT World. Over the coming months, we have several virtual conferences scheduled. We have a Smart Building Cybersecurity as a Service scheduled for December 17th. There's World Expo 2020 site, A Blueprint for Future Smart Cities. That's January 15th, 2020. And we have Distributech in San Antonio. That's the end of January, the 27th to the 30th. And we'll also be attending ARC Advisory Forum in early February from the 3rd to the 6th. Please remember, you can also secure briefings with any of our analysts or our co-founders during any of the upcoming events that we're at around the globe. So make sure to reach out and have a dialogue with us. And a special thanks to our sponsors, Influx Data, for this educational session. And if you have a suggestion for a topic or otherwise, we always like and welcome feedback, so please drop us a message and let us know. And if you like what you heard today, we invite you to subscribe to our newsletter, YouTube channels, and follow us on Twitter at IIoT_world. This concludes our program for today. Thank you for attending, everyone.